both descriptive and analytical, and also from the analytical one, both observational and experimental studies. Now, we'll be wrapping up that section today by looking at what we call the validation of findings. So, using any of those analyses, then how do we really validate our findings? So when we talk about validation of study findings, we really look at three different explanations, what we call alternative explanations. These are bias, confounding, and then the third one is random error. I think random error, standard error, you know it. We also, I think you know how to calculate the standard error. But we'll be looking at these three different alternative explanations of our findings. Bias, when you just look at the word, it is really an error. But in study design or in studies, it's an error that is committed by the investigator. So it can be unintentional or it can be intentional. It doesn't matter, but it's an error that is committed by the investigator. As I said, it can be unknowingly or knowingly. It's all the same. It's just a bias. Confounding, on the other hand, is a natural mixing of effects between exposure and disease. The mixing of effects between exposure and disease, and the third variable that we call a confounder. So what we normally do in designs, in analytical study designs, as you know, we have what? We have exposure and outcome. Now, what we have in mind is what? The two are related or associated. But if there is a third variable that we are not considering, but that variable either associated to the exposure or the outcome or the disease in our case, then we say the study is confounded. So an example that I quote here is the association between exercise and heart disease. That is a common phenomenon, as you know. We assume that when we are designing this study, for example, we look at what? People who frequently exercise and those who don't exercise. And then you follow them, or you look back into what? Whether the heart disease differs in the two groups. So you assume that all characteristics that these people who frequently exercise and don't exercise are all the same, except that physical exercise, which is one group in sedentary and the other frequently exercise. But the issue comes if the two groups are what? Different in their smoking status. As you know, smoking affects heart disease. So if these groups are already different in terms of what? Their smoking status, then the study will be what? Confounded. So that's what confounded. So smoking in this case is what we call a confounder variable. We are not looking at it, but we are looking at it what? Whether exercise, a lack of exercise affected disease. But if people who do not exercise, the majority of them smoke compared to those who exercise. Or if people who exercise, majority of them smoke compared to those who do not exercise, then the study is confounded. So these two explanations are what we call, both together, we call them systematic error. Bias and confounding, they are called together systematic errors because they arise from what you can really, or the process that you can see. So it's right from the discernible process. So if you look at the study, you can see that what? If the investigator committed any error, knowingly or unknowingly, and also if the investigator didn't account for that confounding factor, that is something that you can see. So we call them systematic error because they arise from a discernible process. The third explanation of finding is what we call random error. That one arises from chance. So there is really no assignable cause. There is no way you know the cause of that chance or random error. The cause is not known. As a result, it's called unsystematic error. It's unsystematic. There are two sources of random error. The first one is measurement error. That means if what you are measuring is really not adequately describing, or the measuring procedure is not adequately describing what you are measuring, then it's measurement error. And again, as we have been talking all the time, sampling variability will also lead to random error. So as I said, these ones are really very difficult to avoid. We can minimize them, but it is not possible to avoid random error. But there are three ways to reduce random error. I know when you calculate the standard error, you might have seen how sample size affects the standard error. So increasing your sample size will minimize the standard error. Sometimes I said because there are some measurement errors, repeating a measurement or repeating the entire study. So an entire study might also will help to reduce random error. Again, there is no alternative than having what you call efficient study design. So instead of just reporting like case control study, you better go for what? For cohort study, and then the more powerful one, which is experimental design. So efficient study design will also help you to reduce the random error. So these are really, whenever we are interpreting our study design or the result of the study designs, we look into these three alternative explanations: and bias, confounding, and then random error or standard error. Any question? So I will spend a little more on confounding. Confounding, by definition, is the distortion of the effect of one risk factor by the presence of another. So that confounding distorts the association between what? The risk factor that you are looking at and then the outcome. So the distortion of the effect of a risk factor by the presence of another. So confounder can be what? Either positively or negatively correlated with the disease or the factor. So it can be related to both the factor that you are looking at and also the outcome at the same time. But I guess again, it doesn't affect only one way, but it affects both ways, either positively or negatively. So again, this is the example that I used initially. Heart disease in sedentary and people who exercise frequently. So the assumption is what? This group is similar in all other respects, except what? Except the nature of physical exercise. But what, again, if sedentary people smoke more than those who exercise frequently, or if those who exercise smoke more than those who do not exercise. So this, in this case now, smoking is, as I said, is a confounder. So there are several factors that you can look at whenever you are, when you think that the study is confounded. So age is one, so you have to consider that all the time. In animals, breed, in human race, these are all confounding factors that you need to look at. Gender is another confounding factor. Socioeconomic status, also lifestyle. All of these are confounding factors when you are looking at the association. Yeah. Here, for example, I looked at the effect of obesity on heart disease. This is what you are trying to assess, if heart disease differ between obese people and non-obese people. So, but what is the major cause of heart disease? As you know, what's the major cause of heart disease?
Major cause of obesity?
No, heart disease.
Heart
The major cause is age, isn't it? Age is the major cause of heart disease. So if just you are looking at obese and non-obese people, and then assess heart disease, and as you know, age is what? The major factor in heart disease, the major factor in disease. But if obese people are what? Either older or younger than non-obese people, then these people are what? Already at a different risk of heart disease. So age is what? Age is the confounder both for obesity and heart disease. As you know, young people are not obese most of the time compared to adult or aged people. So in this case, age is what? Both the confounder because it affects obesity, at the same time it also affects heart disease. There are several ways to control for confounding. We can control at the design level when designing our study. We can also control in the analysis. So control in the design involves what we call restriction and matching. We can also control by just randomizing our study population during the design, but we can also control in the analysis. So you have a lot of actions to control for the confounding. As I said, in the design, you can just randomize your study population so that you have a fair distribution of that variable in both control and the exposed group, or in the treatment and control group. So you randomize that one. By randomizing, you have what? Almost equal level of that confounding factor in both control and study group. You can also restrict that factor, like in narrow range of values. Here I put, for example, white males age 35 to 54. So you limit your study in that group, white males age 35 to 54. So the age is restricted here. At the same time, so you don't have confounding age as a confounding factor. You also have what? Only males in the study. So there is no sex as a confounding factor. Also, we are looking at what? Only the white people, so race is not a confounding factor. So that is what we call restriction. Restriction within a narrow range. So whatever you account from this study will not be at least confounded by race, by sex, and by age. So that's what we call restriction. You can also match the study, the exposure and control group, or the study and control group. Again, matching means if you have, for example, white male age 35 to 39 in non-exposed group or in control group, you also take the same white male age 35 to 39 in the exposed group or in the treatment group. So you are matching the age, sex, and race that you have in the control group. You match that one with what you have in the exposed group or in the treatment group. So that is matching. So you have the same race, the same age, and also the same sex in both control and the exposed group. So this is what we call matching. So these are what you can do at the design level, at the design of the study. If you are not able to do this in the design now, you can control for that confounding in the analysis. We have what we call stratified or stratification analysis. That means you stratify your data based on what? Based on these confounding factors. And then there are several statistical or analytical tools that you can use in order to analyze such data. So Mantel-Haenszel odds ratio is one, and the other is the standardization, which is both direct and indirect standardization. Because stratification involves, drawing a lot of tables. It's really not that hard in terms of what we have been doing before, but you have to do several tables, so that will take a lot of time. So we are not cabling these two measures of analysis. But for MPH students, we already looked at multi-lensing odds ratio. And then after this class now, we can also start standardization, both direct and indirect standardization. It's not really that tough as a methodology, but as I said, you have to draw table for each level of what? For each level of confounding factors. So it just takes too much time.
Did you say mental Hunt's odds ratio is direct and indirect?
No standardization.
Oh, then what's the odds ratio?
You have the name there. Maintenance.
I don't know.
Pardon?
Did you explain what it is? Did you describe it? I didn't hear that
It's
part.
analysis method. It's analysis method what you use in stratified data. That means you first stratify your data. For example, here what we have what? White male, age 35 to 39. So what you do is what you have white male here in non-exposed. Similarly, you have white male in exposed. You also have white male age 35 to 39. You also have in exposed 35 to 39. So you stratify your data based on these factors. So you are draw is not really the data to 2 by 2 or 2 by 10. You have separate tables for all of these factors. Then when you're analyzing, you use multi-lensing odds ratio. It's not just one odds. All of them you can have, for example, in this case, you can have 6 different tables, but you report one result. For that one result is multi-lensing odds ratio. So again, looking at bias or systematic error, this is again any process or effect at any stage of a study that produces result or conclusion that differ systematically from the truth. So again, bias is really not only during study design. It can be during study design, it can be during conduct of the study, or it can be during reporting. So all the same. So any process at any stage of a study that produces results that are systematically different from the truth is what we call a bias. So it is an error committed by the investigator. So there is no way of really minimizing this design except by what? Proper design and execution of the study. So even if you increase sample size, if you improve your measurement procedures, all don't help, and it's only by the proper design and execution. So most of the time, really this type of conclusion arise during reporting or during conclusion of the study, because people sometimes just report what they want to report. But it's all the same, even unknowingly, if it is occurring unknowingly by the investigator or unintentionally by the investigator, but it still leads to what we call result that or conclusion that differ systematically from the truth. So it's only by the design and execution that we can improve systematic error. So what is the difference between bias, systematic error, and standard error or random error? Systematic error is lack of validity. That means the finding is really not valid. If you see that there is a bias, either by confounding or by any kind of error, then that disqualifies or invalidates the findings of the result. So again, as I said, you cannot reduce by increasing your sample. You just multiply that error. If you increase the sample size, you just multiply that error. Standard error, on the other hand, is lack of precision. It may not be precise, but it is still what? It's still valid. So this is just lack of precision. And as you know, one way of reporting lack of precision by calculating that confidence interval. So that confidence interval indicates your lack of precision. So this lack of precision can be minimized by increasing your sample size. So if you increase your sample size, you can better describe what characterize your findings. So standard error can be reduced by increasing sample size. Systematic error cannot. And again, as I said, one is a lack of validity, the other one is a lack of precision. So bias, there are three major categories. Confounding is one, as I said. There can also be selection bias, measurement or information bias. So these are the three broad categories of bias or systematic error. Confounding, I think I talked about it already, but selection bias is a systematic difference in the characteristic of study population and general population. So if, you know, as we said, we are always, in order to characterize the population, we take sample and analyze our sample and then infer back to our general population. So if our sample is already different from general population, so that is what we call selection bias. The sample that we take from the population is already different from a general population. So there are several ways in which selection bias occurs. The first one is in case control study. This is always very prone to bias because it's, as we know, this is retrospective data.